Welcome. We begin chapter 3, which is titled Describing Data. And we'll start with describing what's called a measure of central tendency. So a measure of central tendency is a value that attempts to describe a set of data by identifying the central position of the data set as representative of what we would call a typical value in that data set. And there'll be more than one way to describe this central position. We'll be talking about 4 measures of central tendency: the mean, the median, the mode, and the mid-range. And the choice of which one to use to attempt to describe a typical data value varies by situation. So for now, we'll jump into starting here with the mean. So the mean commonly is referred to as the average, numerical average, and we will this semester use those interchangeably. So mean or average of a data set, and we will find the mean in a moment, but I first want to talk about symbols. So if we're able to gather data from an entire population, then the symbol that denotes that size of our population will be capital N. If we are relying on sample data, so we collect a subset of the population, then that sample size is indicated with a lowercase n. So just a reminder over here, parameters. So parameter is a measurement obtained from population data if we are able to access an entire population, as opposed to a statistic is a measurement obtained from a set of sample data. All right, so 2 different symbols here. And then any value in a data set will be using X to represent a data value. And then when we start finding the mean, again, we'll have to differentiate between examples where we're looking at population data versus sample data. So if we have a population set of data, the population mean is denoted with a lowercase Greek mu. So that's what a mu looks like. I'll just write that here. So it doesn't have to be perfect, but the idea is that this line, vertical line on the left, sits below the line we're writing on. And then it kind of looks like a U. It sits on the line. And then it finishes off there at the end. So that's a Greek mu. So that will be our population mean. But if we collect only sample data, then we have a separate symbol for the mean, and that we call X bar. So X bar is written as an X with a bar over it. Okay, so let's step through some examples where we find our population or sample mean, and then we'll talk about these formulas. All right, so number 1, I have 4 chocolate chip cookies for sale, and the number of chocolate chips in each cookie follows. All right, so they didn't mention taking a sample, so it's just the 4 cookies that are for sale. So we're assuming those are all the cookies for sale. So population data. So I have a cookie with 10 chocolate chips, one with 7 chocolate chips, one with 5 chocolate chips, and one with 14 chocolate chips. And this image is trying to convey that information. So this first pile of chocolate chips, so that would be the cookie that had 5 chocolate chips. And then a cookie with, those are 7 blocks there, 7 chocolate chips. And then the next one is 10 chocolate chips in that cookie. And then the last one has 14 chocolate chips. So I would want that cookie, 14 chocolate chips. Okay. So let's start with what we'd like to do. So I'd like to describe the number of chips in a typical cookie by finding a population mean. So we're trying to use one value, the mean, to try to describe this data set the best we can. So our population size, so it's capital N for population size, and I've got a total of 4 cookies. And I'm going to look for the population mean. So the symbol is our lowercase Greek mu. And to find a mean or a numerical average, we add, so that's our capital sigma, each of our X values, and we divide it by the number of data values. And in this case, that would be represented with a capital N for our population size. Okay, so let me talk about what a mean is doing. So what we're doing is when we add these X values, we're taking all the chocolate chips in total in these 4 cookies. So if we add up all the chocolate chips in each of the 4 cookies, so if I could remove those chocolate chips and put them all in a pile, that would be my numerator. And then what I do is take all those chocolate chips and spread them equally among those 4 cookies. So that's what's happening with averaging. You're spreading out those values equally. So I'm going to head over to my calculator and I'll just type that numerator in, 5 plus 7 plus 10 plus 14. So I'd have a pile of 36 chocolate chips. And if I spread them out equally among those 4 cookies, then I would have an average of 9, and I'll write the units here. This will be 9 chips per cookie on average. So if I could reshuffle the chocolate chips, I would change them into piles here, 9, 9, 9, 9. So rather than looking at the variation up top of 36, with each pile being different, it's just saying if we put 9 chocolate chips in every pile, we'd still have our 36 chocolate chips, but they'll be dispersed evenly among the 4 cookies. So I'm doing chocolate chip examples, but you could also think of it maybe as quiz grades. So if a teacher gave 4 quizzes and those were your scores, you would be looking at a mean, an average of 9. And so it's an attempt to describe just what is typical. So obviously not all the cookies have 9 chocolate chips. In fact, none of them do, but it's our attempt to describe what we would call typical for the data set. Okay, so let's switch to number 2. Now it says 4 cookies are selected at random from a bin. So now they're not picking all the cookies because it says they're selecting some. So we're going to be looking at sample data, but the values here are actually the same as above. It's just symbols that are going to change. So if it's a sample size, it's lowercase n. There's still 4 cookies. And the sample mean is the symbol X bar. So we would still add up all those data values. And then we would divide by, now it would be lowercase n for sample size. But numerically, the calculation is going to be the same. So I'll write it again. We would still just add the data and divide by 4. So it's still going to be 36 divided by 4. It's still going to be 9. So the numerical answer is the same. The thing we want to be sure that we're getting is that the symbol changes for populations versus samples. Okay. So now number 3, now it says Henry bakes 4 chocolate chip cookies and the number of chocolate chips in each cookie follows. So if it does not mention a sample, we're assuming that that's all the cookies that Henry baked. So Henry is a very consistent baker. Every one of his cookies has 9 chocolate chips. So as we're focusing here on symbols, you'll ask yourself, do you have population data or sample data? And in this case, and it's the 4 cookies he baked. So if it doesn't mention sample or random selection, we always assume we're talking about the entire population, all the cookies he made. And the mean then would be mu for population mean, symbol for the formula then mu equals sigma x over capital N. And now, if all the data values are 9, when you add up those 4 numbers, we already did it above, that's going to give you 36. Divide by 4 is again 9. So if all the data values are 9, the average would have to be 9. So 9 chips per cookie. So even though the data sets are different, the numerical value for that average is the same. So the mean doesn't tell you everything about a data set. it doesn't tell you that these are all the same and there's a variety here. So not only are we usually interested in the mean of a data set, we also are going to later find a way to express the fact that this data is perfectly consistent and there's variation in this data. All right, one more. All right, chip counts for a random sample of 4 chocolate chip cookies follow. So this is definitely a sample because it says sample. So our formula and our symbol here, so X bar for sample mean, and we add the data and divide by the number of values. Now, the reason for this example is I did want to show you that we're being a little bit casual with our notation. So each one of the cookies we could indicate using subscript notation to say the first cookie, the second cookie, the third cookie, and the fourth cookie. So those subscripts 1, 2, 3, 4 indicating each. But we tend to just, again, be very casual and just use X without putting the subscripts. And then if you've used summation notation before, you'll also know that we're being very casual here with our sigma. We don't include any what are called indices of summation. And if you haven't heard that phrase before, that's okay. We will just indicate adding data values again by saying sigma x. So now this is kind of a weird batch of cookies because the first cookie has no chocolate chips. That's not a wonderful cookie. And then just 1 chocolate chip and just 1 chocolate chip. And then that last cookie has 34 chocolate chips. So I would want that cookie. It's just basically one big pile of chocolate chips. But what we're going to see when we take a look at our average, all right, so our average here, if I were to add up those values, I would have no cookies or no chips in that cookie. There was 1 chocolate chip, and then finally 34 chocolate chips. But what's going to happen again when we divide by 4? This is still 36 over 4. So this is still an average of 9. So in that case, I really wouldn't say that 9 is a good indication of what is a typical cookie in this data set. So sometimes the average is a little bit misleading, and we'll talk more about that in a bit. But the summary here is that different data sets, that data set, and then that data set, they can all have that same average, but we'll have to learn how to discuss more about a data set in terms of showing that those data sets do differ in terms of how much the data varies. All right, and we'll end there with our chocolate chip cookies and discuss other ways that the measure of center can be calculated aside from the mean. So we move forward and discuss the median, mode, and mid-range as other possible measures of central tendency.